For IQE5, a school wants to replace piping in its bathroom to improve the flow's consistency. The initial pipe has wear but isn't extremely rough on its surface. The new pipe is brand new and smooth with a bigger height up, so they had to raise the sinks and toilets. What would happen to the flow type and the head loss by replacing the pipes? So, if the flow is considered turbulent, replacing the pipe for a smoother surface wouldn't make the flow laminar, as the Reynolds number is independent on the roughness of the pipe. The head loss would increase because there would be more height to pump the fluid up the pipe to overcome frictional losses. So then a farmer is laying a channel to feed water to his crops. He laid down a 20-meter long channel with a width of 3 centimeters and notices that the water level at full flow is only 2 centimeters in height. The average velocity is zero point 0.6 meters per second, and the temperature on the current day is 35 degrees Celsius, and the atmospheric pressure is 1 atmospheric. Determine the change in work required for the water to overcome the frictional losses. So what we know is the velocity, the diameter or the width of it, the height, the length, the temperature, and the pressure. And we need to find overall the work, but the pressure change, hydraulic diameter, volumetric flow rate, and area are needed to solve for the work. We can assume the open channel, so pressure of the gauge is equal to the pressure of a temp of atmospheric. The flow is steady and incompressible. Interest effects are negligible, and there's no bends, valves, or connectors, and no work devices. The properties using the 35 degrees Celsius and the 1 atmospheric, where you get density is equal to 999.7 kilograms per meter cubed, and the viscosity is 1.307 times 10 to the negative third kilograms per meter times second. And so we solve for it. First, we find the diameter of the hydraulic diameter, which is equal to the equation shown, and we get 3.428 centimeters. Then we find the Reynolds number by taking the density times the velocity times the diameter, hydraulic diameter, over the viscosity, which gives us 15,732. With that, that means the flow is turbulent. Then we find the frictional loss, which is 64 over the Reynolds number, which is 0.004068. So now, to find the delta P, we take the frictional times the length over the hydraulic diameter times the density times velocity squared over 2. Well, this is equal to 0.427 kPa. The area then is just 2 centimeters by 3 centimeters, the cross-sectional area. So we get 6 centimeters cubed. Then to find the volumetric flow rate, we take the velocity times the cross-sectional area, which is 0.6 meters per second, times 0.0006 meters squared. And so then to find the work of the pump, you plug in the volumetric flow rate times the delta P, and the reasonableness is that it's not too reasonable on an open. It's a little unreasonable on an open channel, but the Reynolds number is accurate as it typically have turbulent flow due to the size of the channel.